Hi everybody, my name is Yuan Sun. The topic of my speech today is deep reinforcement learning based beamforming in RIS-assisted MIMO system and hardware loss. I will cover the following 7 sections below. So first, I will introduce the background of this paper. Reconfigurable Intelligent Surface RIS is an imaging technology that is widely recognized as a fundamental technology for the forthcoming generation of wireless communications. Considering the increasingly intricate radio environment, traditional optimization algorithms have become impractical for their complexity. However, with the continued advancements in hardware decision, computers now possess significantly enhanced computing capability. Consequently, a new alternative algorithm called reinforcement learning has emerged as a method for machine learning based RIS-assisted communication. Then let's talk about the work of this paper. In this paper, a deep reinforcement learning DRL approach is used for the RIS beamforming decision in the RIS-assisted multiple input, multiple output MIMO communication to maximize the system summary in the downlink transmission. The main contributions of this paper are summarized as follows. We consider the hardware loss and purpose of phase shift decision for RIS-assisted MIMO communication. We design a DRL-based RIS beamforming algorithm for the above scheme by introducing interference signals and interfering with action selection to prevent from falling into local optimal solutions. And the simulation results show that the proposed algorithm has a significant improvement over the typical algorithm. Then let's talk about the system model. For the RIS-assisted wireless communication system, the system diagram is shown in Figure 1. With key signal antenna users and one RIS with L elements. Now, the channel model between the base station and the user key can be expressed as HK equals HBSK at sum HBSK times phi times HLK, where HBSK, HBSL, and HLK respectively denote the channel vector from the base to the user key, from the base to the RIS, and from the RIS to the user key. Considering the conditions of hardware loss, the phase-independent amplitude model of RIS can be obtained as phi equal a dike phi e for phi e to phi l, where phi l is equal to CL e to the power phi l. It's the phase dependent amplitude model for each RIS. The phase shift is phi l in from 0 to 2 pi, and the amplitude set phase. The single user channel is aggregated to obtain the multi-user channel, with denote as this formula which h1 equals h small h1 small h2 to small hk hbu 等于 hbs1 hbs2 to hbsk. We will introduce the problem of formulation in two parts: uplink stage and downlink transmission. We first introduce the uplink stage. The base receives the polite signals transmitted by the user key. The polite signal vector received by the BIs is expressed as yk equals h times p at n, where p is a polite pattern. So the BIs use a minimum mean square error to estimate the channel matrix of the received polite signals, that is this formula. H equals YU times P to the power h. So the P times P to the power h is sigma square times I. I matrix is a unit matrix. When P is a unitary matrix, the above examined channel matrix can be transformed. Uh, the, the, the formula is simplified this formula. So then in the downlink transmission, this transmission with zero forcing ZF precoding is performed with the following expression. This formula is the zero forcing precoding, where P normal is normalized power matrix and writing as P normal is equal dig matrix 4. The signal received by the case user is YPK with CKH times HK times XK 8. It sets to the power H times HK times XZ sum and add NK, where SK is a signal sent to the user key, NK is a additive Gaussian white noise. For, for the RIS-assisted wireless communication MIMO system, we will use the sum downlink rate as an indicator to measure the performance of the system. Thus, the problem can be expressed as the max the function is max PM subject to phi in from 0 to 2 pi mu and kappa. Where PM equal RK sum from k equal 1 to k. The signal to interference plus noise radio (SINR) is given as this formula. So we propose the deep reinforcement learning framework. We will introduce the principle of soft actor critic SAC algorithm, and then we present the improved SAC algorithm with the environment parameters. In contrast to typical DIL algorithms, we use the advanced SAC algorithm. The training of the algorithm involves a trade-off between the maximized expected returns and the maximized entropy. The SAC agent consists of 3 networks, 2 Q networks, and a random policy network or actor network. The Q network takes the states provided by the environment and actions produced by the actor network as inputs and produce Q value estimates, which are scalar values. Given a network of actor pi phi parameterized by phi, the Q network is trained jointly in the SAC algorithm as 3 formula. There we use gradient descent. Similarly, the policy network takes state vectors from the environment as inputs and produces these numerical action vectors. The loss function for the policy network in the SAC algorithm is calculated as this formula. For the update of the policy network, we use the static gradient algorithm for policy gradient phi g phi and the gradient ascent algorithm to update and the parameter of the policy network as this formula. Finally, the regularization factor of entropy alpha is a hyperparameter, and a larger value of alpha means that the agent will have a larger exploration space, which enables agent to explore more possibilities instead of being limited to the current action. In IL, environments are usually distinctly into abacido and non-abacidic tasks. So an abacido can terminate when a terminal condition is met. The fall of working payment and reaching a specified number of time steps. The continuing tasks, in contrast, do not have a certain ending point, and the agent roams the environment on an infinite horizon. Since the BS performs beamforming and RIS elements continuously, it is evident that this is a continuing task by nature, where it is possible to specify a set of terminal conditions such as a summary threshold or a minimized number of steps. It might introduce bias and mislead the learning agents. Therefore, we adopt a continuous test framework to develop our approach. So let's introduce three important parameters. The first, action. For the optimization problem, we have contrasted the action of agent is performing decision of the RIS. Since the neural networks cannot handle complex numbers, we need to separate the real and the imaginary parts of the RIS pieces. And the action space contains two error elements. Then the state. To take full advantage of information obtained by the agent in interacting with the environment, we define the state space as the channel matrix H and the RIS fast matrix phi. The increment realize channel matrix and the RIS beamforming. In order to reduce the influence of the calculation of the channel state matrix, we perform a weighting operation on the channel matrix after each environmental interaction. The last, reward. Reward is important to DIL. For each episode, we will use the summaries of the downlink transmission to determine the reward in order to choose the right action to get a higher reward for the agent. So reward is an indicator of my system model. Then for the non-episode test, we can use the average reward instead of its tendency raw reward to allow the agent to learn from the environment as R. R equals R minus R bar. R bar. The engines to enter the state action space where Q prediction is difficult to perform. Thus, allowing the created the prediction error of the unknown or less selected actions as the formula. We're here. Here is a Hanuman project, and lambda in from 0 to 1 is used to restrict the employer network from influencing the policy network to choose the wrong action. At each update step, perturbed actions are sampled from the experience replay buffer inside of the original actions generated by the policy network, and then the loss functions for the Q network and the active network are as follows. This formula is the Q network's loss function. This, and we change this formula to this formula, which a beta I equals a Hanuman project lambda, and perhaps oh no interference. We define the loss function of the exploratory network by maximizing the sum of the absolute temporal difference (TD) errors, corresponding to the two Q networks as to the formula. The deterministic imploration policy gradient is then computed by the deterministic policy gradient algorithm. so the last so then the part is simulation results. So then we will start with the simulation parameters. The BS is equipped with a uniform linear arrow URA that is placed at is 100, and RIS is ULA and located at 010, and the user is equipped with a single antenna and is randomly generated as a circular range. We set the number of the BS antennas at 4, the number of users at 4, and the number of RIS elements as 32. One channel percent includes 2 channel blocks. The parameters of the Q network and the parameters of the RIS hardware loss model are given in table 1. This. To verify the effectiveness of the proposed algorithm, we compare the 3 algorithms: SAC, imploration, and random, and the same configuration. Since the DRL is highly randomized, we conduct 10 experiments and average them in order to facilitate the observation, which makes the results more convincing. In Figure 2, we analyze the influence of different algorithms on the system sum rate compared to the random algorithm. The risk-beamforming decision can significantly improve the system sum rate, and the proposed algorithm achieves the significant improvement over the SAC algorithm. This is because, unlike the typical DRL algorithm, the error in the value function for the proposed algorithm can be corrected by introducing a perturbation signal to interface with the action selection. Thus, the agent may select the optimal action more accurately, and the effectiveness of the proposed algorithm can be verified by the fact and the system sum rate PM is significantly improved. Then we say Figure 3 is effect of different C values on PM at I equals 32. We look the performance of a proposed algorithm for different C is investigated in Figure 3. For the convenience of the observation, we see the typical SAC algorithm as a benchmark. Comparing with Figure 2, it can be seen that the proposed DRL algorithm with C equals 0.6 had a significant improvement in the system sum rate over the SAC algorithm, and it is also observed that the system sum rate PM of the proposed algorithm increases as the value of C increases. The last, we make conclusions. The first, we studied the risk-beamforming decision in the RIS-assisted MIMO communication and proposed a modified SAC imploration algorithm to solve the risk-beamforming decision, considering the RIS hardware loss. 2. The simulation results show that the proposed algorithm is able to realize better risk-beamforming and has a significant improvement in the downlink system sum rate compared with the typical SAC algorithm. The last, concerning the case of MIMO RISes, we will consider the MIMO agent algorithm to solve the beamforming decision problem in the future. Thank you very much.